my interesting area. You know, there are a couple. I think I got that to work. Okay. There's maybe some shares over there and silent. Okay. Yeah, so this community, you know, it's enlarging. There's NeurReps. There are some like related communities that sort of focus on geometric learning. So we have the Graham workshop that we started that I helped organize, and then there's also the TAG ML workshop, which is also sort of this intersection of like mathematically informed machine learning. I just want to quickly note so the Boston Symmetry Day. So like if you like what you hear here, together with Hannah Lawrence and Derek Lim, another student of Stephanie's, and John Park, who's a student of mine, we organized this Boston Symmetry Day workshop in Boston. We're having an informal get-together and poster session. I don't know if we picked a date.
Yeah, we haven't announced it yet. It's the Monday before Thanksgiving.
And then we will also have like a full workshop with like catered lunch and probably like 150, you know, people and lots of speakers in the spring semester, and we'll do another poster session. So if you're interested in geometric deep learning, if you like what you hear today, then join, become an element of the Boston Symmetry group. So, okay. Zoom overlays. Okay, great. Okay, so I'm Robin. This is my student Dian, and I'm going to tell you about pushing the limits of equivariant neural networks. So the kind of problems I'm interested in are the kind of problems that just training giant models doesn't solve well. So I'm interested in sort of scientific domains. I'm interested in robotics. I'm interested in domains where there often isn't enough data to just train a really large model to do well. Domains where data is expensive to collect, domains that are very high dimensional, and domains where the application demands, for example, very high physical fidelity. And we can't really just trust a large model that might easily just go out of distribution and return made up results. So these are the kind of problems I'm interested in, the problems I'm interested in solving. And the approach that Dian and I take to these kind of problems is by incorporating symmetry as an inductive bias into networks. So to take some element of the physical theory and inject it as a hard mathematical constraint into the models. Okay, I suspect that like the other, maybe a lot of people in the room are already familiar with, and to some extent the other talks in the series will have talked about these things, but I'll introduce sort of the mathematical way that we think about symmetry and neural networks. So here I'm interested in some kind of task function, which I call f, and there we go, great. Okay, and here I'm showing f as like a segmentation mapping. So it takes an image and it segments the pixels into their, you know, different classes. And what we want to observe about this ground truth function, we're not talking about a neural network yet, is that this ground truth function is rotationally equivariant. And what does that mean? That means if I take this input image and rotate it 45 degrees, and then I segment it, that's the same thing as if I were to segment the image and then rotate it. So we call this equivariance, right? Similar, the more common word is invariance, where some change in the input doesn't affect the output. Here it's equivariance, so whatever change I do in the input should have a corresponding change in the output space. And there's the math equation that recognizes that. And so when we have a task function or something that we want to model, and it has this kind of property, we've noted that it's equivariant. And now we want the neural network to have that property too. So here's my picture of a neural network with all of its linear and nonlinear layers. And I've noted that there's this group G that's acting on all these spaces. And we want to constrain the layers to have the symmetry. So we imagine that there's some group action, some transformation on the layers. And what we find is that we can create some sort of weight sharing pattern in the weights of the layers. And that will constrain the neural network to have the symmetry that we just observed in the task function. So there's some sort of mathematical constraint. We solve it. It results in a certain pattern, mathematical pattern in the weights of the neural network. And then the neural network will have the symmetry built in. Okay, and so visually, you know, like what I like to show people is that this is a mathematical constraint on the weights of the neural network, whatever those weights are. So that means that it holds true at all times during training. and for all values of those weights, right? On the one hand, I could pass in this image of the tiger, and it will correctly have the rotational symmetry that I showed, but I could also just pass in noise, and the noise would also be constrained to rotate the same way. It's all inputs at all times during training. It's a hard constraint. Okay, visually, I like to represent it with this sort of picture, right? Which is that we have observed that our true function that we're trying to find is this point here, lives in the space of equivariant models. It has this mathematical property, right? And so we're going to constrain our search space, our entire training regime, to be within this subspace of models that also have that property. So instead of having to learn the symmetry, we start with the symmetry built into the model, and we'll have it throughout training. Okay, and so, as you might imagine, symmetry is a big part of physics, and so this has had a huge impact on a lot of different physical modeling domains that we've done with neural networks. It's drastically improved our efficiency and our physical fidelity. So I'm going to touch briefly on just a couple of these, and then in the second part of the talk, Dian is going to tell us a lot about robotics applications, which has really turned into a really killer application for equivariant neural networks. So let me just give you a flavor of how this works high level. So one of the domains where we applied this was fluid dynamics. So machine learning for fluid dynamics has evolved into quite a large area and has important connections to climate science and weather prediction, which is a huge area. And so here's how our framework works in this case, right? So we say, okay, we want to model fluid dynamics. What are the differential equations, the mathematical models that govern fluid dynamics? Those are the Navier-Stokes equations. Okay, and then we say, what are the symmetries of the Navier-Stokes equations? So they have this Galilean frame invariance, those rotations, translations, and something called Galilean boost, which corresponds to a lack of knowledge of what the zero velocity frame is. And then there's also an anisotropic scaling law, which relates fluids at different scales. Okay, and now we build a neural network that takes those physical symmetries from fluids and builds them in as constraints into the weights. So here I'm showing some visual representation of our scale equivariant model. So there's an anisotropic scaling law, and we've built that into the model. So it doesn't know fluid dynamics yet, but even at initialization, it knows the symmetries of the system. Okay, and then we train it to do the model, and what we see is that compared to other baselines, we're getting much better physical fidelity. So we have different ways, we have different domain relevant metrics that measure the energy at different scales in the fluid. We get much better physical fidelity when we build the symmetries into the network. Okay, here's another example where we did trajectory prediction. So this is for various pedestrians and vehicles, and the goal is to predict if you have a multi-agent system, lots of past trajectories of various vehicle users, and you want to predict the next couple seconds of all the vehicle users around you. You can imagine using a system like that in a self-driving car. It would like to have some uncertainty model about the movements of the other vehicles on the road so that it can be appropriately cautious and not collide, right? And the important thing is that you recognize that this system has sort of a local rotational equivariance, which is if I zoom in on a scene of a couple cars and I sort of look at the couple cars around it, it doesn't really matter which way is north, south, east, or west, or for the most part, it doesn't really matter. That if I have various cars in some trajectory configuration, that same local situation will repeat anywhere I go, and I could rotate it. I should have the same kind of particle dynamics. And so we can train a model, and we get that, right? And I'm showing this little inset picture down at the bottom, which shows that, somewhat alarmingly, if you were riding in a self-driving car and it had a non-equivariant model in it, then without looking too hard through our data set here, it's pretty easy to find examples where the baseline model will predict that some car will turn left, but then if you just take that exact input data and rotate it, so I haven't changed anything, I just changed which direction I called up. That's it, right? It's the same data, I just changed how I present it to the model. And this is a model trained with extensive data augmentation. It will predict that the car is going to turn right just because you changed how you were looking at the scene, right? So that kind of sort of physical inconsistency is not sort of allowable for applications that involve trusting your life to the model. Okay, and then lastly, this is a collaboration with MIT Lincoln Lab where they're super interested in modeling radar signals for object identification and applications. So here what you have is you have, so what I'm showing are these spherical radar signals. So you might have seen like a radar cross section. Basically, I have some object up there, right? I hit it with a radar signal and I get some frequency response, right? And when I think about that object and the object rotating in space, right, I could ping it from lots of different directions and I get a different radar response from any given direction. They're not necessarily related to each other, but what you get is the spherical signal, which is sort of what the radar response would be like from any angle, okay? And there's a symmetry to this problem, which is if I rotate the object and I also rotate the radar dish, the radar receiver antenna, right? Then I should get the same signal, right? But you have to build that symmetry seems basic, but you have to build it into the model. And when you build it into the model, you get much better response. And the name of the game here is that, you know, it's unrealistic to ask the airplane to hold still while you take your radar dish and move it to all the different angles so that you can get a nice complete view and observe it. So you need to be very data efficient in the sense that you only have a couple observations, right? Maybe 3 to work with. And when you use the equivariant symmetry in the model, it drastically improves the data efficiency. So you get much better identifications with much fewer radar signals. Okay, so those are a couple applications of equivariant. What time did I start? Like, we started like 10 minutes after, right? Okay, great. Okay, so equivariant neural nets have been finding lots of applications in lots of domains. But something, and Dian will talk more about the robotics applications, which I didn't mention yet. But I'm actually interested, you know, this is my personal tendency. I'm interested in the limitations, like where things sort of break down and how we can push them further. So, you know, the community has evolved quite a bit, and we found a lot of applications. But, you know, this is deep learning. So this is often, you know, we're training on real data, right? It's a question I get a lot. If I'm assuming a perfect mathematical constraint in my model, right? But I'm dealing with real world noisy data, right? How does that perfect mathematical constraint cope with the imperfection of the real world, right? So here I'm showing, for example, that there could be unknown external forces in my fluid data, right? You know, maybe I'm working with like perfect simulation data in high resolution, but maybe actually like I have some estimated velocity fields that come from some like, you know, captures in some wind tunnel with some noise particles, like some particles and lasers, and it's extremely noisy, right? Maybe I'm dealing with just like, you know, we applied this to sea surface flows where I can't hope to understand all the dynamics in the system, right? There are forces and boundary conditions that are not available to me that I don't know. And then lastly, this picture of the ducky is showing that the observations I have, right, may not be exactly the observations I want for symmetry, right? In this case, the duck is rotating sort of out of plane. So I'll say what that means in a second. All right, so what do you do when the symmetry is not exactly mathematically perfect? You want the model to be robust. Okay, so I'm going to present 3 options in the next few minutes. Okay, so the first option I feel like is, you know, it's surprisingly simple. It just basically says, just ignore this problem. And this is maybe partly a thought exercise and maybe partly a suggestion, which is what if I just ignore that the symmetry is not perfect in the data? How well will a mathematically constrained model do if it doesn't perfectly align with the symmetry that I see in the data? So here's our example. This is like a real example that helps motivate this question for us, which is that when we talk about rotational symmetry and image observations, we're talking about, you know, Python image library .rotate of the image. Okay, so you're rotating an image. Okay, but the symmetry in a system like this, that would correspond to rotating the duck from a top-down view. But we often can't observe the duck from a top-down view for a very simple reason, which is that's where the robot arm is, right? So we often are stuck putting the robot arm, like the camera, like 15 degrees off. So we have about a 15-degree mismatch between the kind of rotations that the model thinks it is trying to reflect and the actual rotations in the observation. Question, how much does that 15 degrees hurt performance? Does it mean that we should give up on the equivariant modeling, or is it actually going to work out okay? All right, and so we just tried, right? And our method is this blue line here, right? And the higher it gets, the faster it's learning, right? And so what you can see is compared to these baselines, which are all which are not equivariant but incorporate symmetry through data augmentation, our model is learning to do these tasks a lot faster, despite the fact that it's a slight side field, right? And we also explore other kinds of what we call symmetry corruptions, so problems with the symmetry in the observation. And we find that, we've entitled this paper, I think, The Surprising Effectiveness of Equivariant Models, is that the amount of breaking that needs to occur before performance starts to degrade is surprisingly high. Okay, and so we wanted to think about this. We were like, okay, like, we're happy that that happened, but like, what's going on here? Why does the model still work even if there's a mismatch, right? In this approximate symmetry case, right? And we thought about it, and we surveyed the literature, and people use the term approximate symmetry a lot. We kind of found out that there are different things people mean when they say approximate symmetry, and some of them are bad, and some of them are not bad, and some of them are sometimes bad. All right, so this picture is showing this top is correct symmetry. So here you have a task function f, okay, and you have the probability distribution of the data p. And that's perfectly reflectionally symmetric. Everything's happy. That's the equivariance case you have in your head. Then we have this incorrect case. So here, notice that the function f is simply not symmetric about that line. We call this incorrect symmetry. But we found, and this is what people often picture when they say that there's a symmetry problem, but in many, many cases of approximate symmetry, you're really looking at this bottom picture, which is what we call extrinsic equivariance. And in this case, it's not, what's happening is that the data distribution itself is not symmetric, right? And what that means is when I apply some symmetry constraint, it's not that it's forcing the model to give wrong answers, it's that it's forcing the model to generalize to out of distribution data in a particular way. Okay, so in the case, so basically we have to handle these cases separately. So in the case of incorrect equivariance, you can examine the question theoretically, and you can basically prove that this comes down to how much incorrect equivariance is in your distribution. So when you deal with noisy data, right, it's not a purely one case or another situation. You can have a little of all of these cases, and whether you should still use the equivariant model or not comes down to how much incorrect symmetry is there, a lot or a little bit. And you can actually compute this crossover point on this plot right here. So this red line is the, so this blue line is the unconstrained model, and the red line is the constrained model, right? And what you can see is as you dial up the amount of incorrect symmetry, there's a crossover point. So in the real world, there's always some mixture of these things. And when should we use an equivariant model? Until, and this is not a thing I can compute ahead of time, unfortunately, it's just something to experiment, but there's a certain amount of incorrect symmetry that can be in your domain before unconstrained models perform better than constrained ones, okay? And you can compute, theoretically what this bound. So that theoretical bound that we're computing here is this green line. So you can see that it doesn't, it's an upper bound on performance, and it will force the model to perform poorly. Okay, and then in the case of extrinsic equivariance, this case where the symmetry is about out of distribution data, it's a mixed picture. So when you're in this extrinsic case of symmetry mismatch, sometimes it helps, sometimes it hurts, and it's difficult to tell. So in the robotics case, it helped, and in this sort of synthetic case that we built, it can hurt. And we thought kind of we wanted to think pretty hard about what is going on here. And I think this bird's picture is my best example for people of when is symmetry hurting you, okay, this constraint. So here's a picture of a nuthatch bird and a woodpecker, okay? And technically identifying, this is like a real data set, identifying these birds from these pictures is a rotationally invariant problem. Okay, that nuthatch, if I rotate the image of the nuthatch, you can still tell it's a nuthatch. It's still, I didn't change what bird it is by rotating it, right? But here's the thing, if you look in the Autobahn guide or mass auto, bird identification guides, they will note that nuthatches tend to walk down the tree. This is like, if you Google nuthatch and look on Google image search, most of the pictures are going to be the bird facing down the tree. So it is not incorrect to impose rotational invariance when studying this problem. But if you do, the model will no longer be able to tell which way the image is oriented, which means that the information which was contained in that pose that helped perform the classification task has been removed and made the task potentially harder. So that's when symmetry is hurting you. So I think like the point of what I'm saying is, there's different kinds of approximate symmetry, and you can think about, when it's going to be a harmful thing or when it's going to be a helpful thing to impose these kinds of symmetry constraints. All right. Yeah, that's mostly, I want to, I'll maybe mention, I think, one more thing I want to say. Okay, so here's another option besides just ignore the problem for how to deal with approximate symmetry, which is to take those hard mathematical constraints that we imposed in the beginning and actually loosen them so they're not so hard. Okay, so you remember this picture that I showed earlier of the perfectly equivariant models and sort of the unconstrained models. So here what we're saying is that the true function doesn't live in that exactly equivariant place, but it's nearby. And so can we imagine a class of functions where there are symmetry constraints, but they're relaxable? So there's some bias towards symmetry, but it's not hard, right? And so here's the relaxed steerable convolution. So without getting into it too much, we took an exactly equivariant formulation, which is this thing on the right from Taco Cohen 2016. And we added this little thing in red, which breaks the formal mathematical symmetry of the convolution, right? Basically, if you want to think like a CNN is shift invariant, if you had some little dependence on the actual location you were in the image in your kernel, that would break the shift equivariance of the convolution. Visually, you can see this is an unconstrained 7x7 kernel. Here's an equivariant kernel. You can see the approximate equivariant kernel. So it provides some bias, but it can break, right? And then when you apply it, in this case, to fluid dynamics, where there's some symmetry breaking in the data, it dramatically improves the performance. So our model is that green curve there. And then this is a paper that we should be hopefully in the archive later this week, in which we apply relaxed equivariant models to reinforcement learning in different in this case, control environments where there's some symmetry breaking. So, in my head, if it works well for dynamics prediction, then it should also, work in a control setting as well. All right, and now we'll head on to the end.
All right. Thanks a lot, Robin. Right, so Robin have talked about all of the cool words about the foundations of academic learning, but I come from a robotic background, so I'm a student with Robin as well as Robert Platt and Northeastern that work initially on robotics, and then when I met Robin, and I saw like a similar talk like this, we started to think, oh, can we use this type of Equivariant model to improve robot learning or not? Because in robotics, data collection is really a very expensive procedure. So for example, in this 2018 work, they actually took folks at Google 4 months to collect 800 robot hour data from 7 robots in order to train a very simple picking policy. Even though the end policy worked very, very well, this is extremely expensive for standard lab settings. Or if we think about, some household robots, it's very hard to imagine that the robot will require hundreds of hours of training post-delivery, right? So like Robin said, in many problems, data efficiency is really the key, and we want to improve that and learn something with fewer samples of data. So, just following what Robin said, so we try to leverage symmetries in robotic manipulation to improve the sample efficiency. And here's an example for why that makes sense. Let's imagine that we have a robot that is trying to pick up the green trapezoid on top of a table, right? So now if we think about a rotated scene where all of the objects rotated on the table, now we will want to execute the exact same graph as before, but in a rotated manner. So those two different scenarios are just 90-degree rotated versions of each other, but previously folks in robotics, we would just treat them as 2 separate samples and learn from them separately. So what if we can use the method that Robin said to design algorithms that can automatically generalize over symmetries in robotics, right? That way we can dramatically improve sample efficiency because once the robot learns from the left state, it can automatically generalize to the right state and to all of the rotated states. So using that methodology, we were trying this in various different problem settings. We started from reinforcement learning, and then we also had some works in behavioral cloning, grasping, and pick place. In all of the cases, we were able to see a very dramatic improvement in sample efficiency compared with the prior works that doesn't include this kind of bias. Experimentally, we were very successful as well. For example, this is a very complex bagel baking task where the robot will first need to open the oven, pull out the tray of the oven, pick up the bagel, put the bagel on top of the tray, close the tray, then close the oven. It's extremely long time horizon. So previously, you might need like hundreds of demonstration in order to train this complex policy. But our work can actually just train it within 60 demonstrations. And similarly, we were also able to train different tasks with the same model. But again, like always a reasonable amount of data, not like 600 hours worth of data. Instead, we just require like 100 or even less than 100 data, which can typically be collected within 1 or 2 hours. Okay, so in my part of the talk, I'm gonna briefly talk about 3 different approaches where we could, incorporate symmetries in robot learning to improve sample efficiency. The first 2 are gonna be reinforcement learning, and the last one is gonna be behavioral cloning, where we learn from human demonstration data directly. All right, so let's start with the first one, the Equivariant actor graded model. So basically, the idea is very simple. We just take the policy network and the Q network, which is the value network in reinforcement learning, and then we enforce symmetries in both of the 2 networks. For the policy network, what we want is that if we have a rotated scene, we want the policy to output a rotated action, right? For the Q network, if both the input state and action are rotated by the same amount, we will expect that the optimal Q value stays the same. So we basically incorporate this equivariant property in the policy network, and then incorporate this invariant property in the Q network. So after we can enforce such symmetric property in that network, we do need to learn from the rotated samples. And here's a example like training procedure comparing our equivariant stack, which is a somewhat popular reinforcement learning algorithm, versus a conventional stack where the network are not constrained, right? So we can see on the top left that equivariant stack can learn this drawer opening task within 1,200 of training steps, and it can reach 100% success rate. But the conventional stack can only reach a 20% success rate after the same amount of training. Quantitatively, we can see that in various different tasks, equivariant stack, which is the blue line on the top, can learn to solve those tasks very fast, whereas the other baseline methods back in 2022 were not able to solve the task very quickly. So this is maybe it looks simple, but actually in reinforcement learning it's quite challenging because we have a very large state space. We were using image observations. We also have a relatively large action space. The action space were defined to control on the delta XYZ of the interfactor, as well as the top-down orientation, and the open close of the vector is quite large of the action space. Also, the reward is sparse. You only get a positive 1 reward after finishing the task. So the baselines really struggled on solving those IO tasks, but by injecting symmetries, we were able to learn them very, very fast. We also tested with more challenging tasks like pick place or the corner picking, which is, the robot needs to nudge the object out from a corner and then pick it up. We can see that in those more challenging settings, our model showing blue were the only one that was able to solve those tasks. So, after we saw this result, we were very excited. This is, some advancement that I have never seen in previous method. So the immediate question that I was asking myself since we have, such a good sample efficiency, will we be able to train some robot policies in the real world directly? Because previously, typically what people do is that we train policy in simulation, and then we do something to real transfer to apply the policy in the real world. So in the following up work, we were trying to do some reinforcement learning in the real world directly from scratch. So there's no sim to real, no pre-training at all. We basically just initialize the network and then try to train RL in the real world conditions. So we were considering 4 different tasks here: block picking, block pushing, collateral grasping, and blocking ball, which is the pick place tag, the one to pick up the block, place it in the ball. And we were able to actually solve those tasks within just 1 hour of training in the real world. So the blocking ball actually required a little bit longer time because resetting the environment was a little bit harder. But again, it only required 2 hours and 40 minutes. We also tested our Equivariant stack with the best performance baseline in the simulation. And then, both of the methods here are trained in the real world. And we can see that, our methods were able to solve the task within 2,000 or 4,000 training steps. But within that short of a training procedure, the baseline were not able to solve this task. And here's an example run of the collateral picking. At the beginning of the training, the robot is basically just doing some random acceleration. We are doing RL, so you need to explore by itself. And then after a while, we reset the environment because we didn't want the robot to stuck in the same failure mode for too long. And just now it reset again. And after a while, I finally got the first successful episode. They pick up the dog toy, and then starting from that successful trajectory, can gradually improve its picking strategy. And then we will see that at the end of the training phase, you can, very stably pick up all of the objects in front of it. Great, so that's the first one, the Equivariant actor credit model. And then in the second part, I'm going to talk about a different approach where we were doing Equivariant cube learning. So in the first part, we were defining the action as the delta movement of the gripper. Another very popular setup is to define the action as the target pose for the end effector to reach to. Right, so for example, here we can define the action as a target XY translation and theta top-down orientation of the gripper, and then use motion planning to guide the robot to actually reach that pose. So in this way, the action can be more expressive. So it's gonna require less of an action step to finishing on the same time. But they have pro and cons, those different action space. But we were just trying to explore the symmetry in different problem settings. So typically in this setup, what we want is a network that is typically a fully convolutional network. This network will take in a top-down image of the scene, and then it's gonna output a set of different cube maps. So first of all, each pixel in those output cube map is gonna be a translation for the gripper, right? So we can basically map each pixel back to the 3D location in the scene and then execute some action. And then each channel of the cube map is going to represent different gripper orientations because we want to control both the orientation and the translation of the gripper. So in this particular example, the first channel will represent, let's say, a 0-degree orientation where I perform the grasp this way. And then the second channel is going to be a 90-degree rotation where I perform the grasp that way, and so on and so forth. And in order to apply Equivariant network here, we need to think about what happens if I rotate the scene, right? So if I rotate the scene, what do I expect my optimal Q value to transform? So first of all, obviously, all of the Q maps should perform a rotation the same as the input, right? Because if I rotate the scene, the object in the scene is rotated, so the Q value for each of the translation action should rotate accordingly. So that's going to correspond to a rotation of all of the Q maps on the output. But that's not yet, because what was originally 0-degree is now identical to 90-degree rotation in the rotated scene. And what was originally 90-degree is now 180-degree, and so on and so forth. So there is this one-to-one mapping that exists in the different channels of my output, which means the channel of the output should perform a circular shift. So if you work with Equivariant models, you might have noticed that this is exactly what we call a regular representation. Right, so that leads us to build a Q network that's using the regular representation of let's say C4 or C8 as the output of the network. So similarly as before, another advantage of this approach is that we can leverage both the rotational Equivariant from let's say Equivariant models or steerable ENNs we can also leverage transition equivariance via fully convolutional model, right? Because this is a UNet, fully convolutional UNet, which means there's no FC layers to break the symmetry from a translational perspective. So the entire network is going to be SZ2 equivariant rather than just rotational equivariant. So like before, we were testing the network in various different tasks. This is back in 21. So you might see like this COVID task which turned up. So, back in 2021 and Northeastern, we had to do one COVID test every 3 days, I think. Yeah, the bad memory is coming back. But again, just focusing on the results, we can see that we can first of all, we can dramatically outperform all the baselines. And if we compare the blue line on top and the green line on the bottom, the only thing that we change is replacing the standard convolutional network into a correctly identified equivariant model. So this is a very simple change that leads to a dramatic improvement in sample efficiency. And following up, we used a similar model to solve grasping. So this project is led by my lab mate Xupeng Zhu. So basically, we try to ask the robot to learn how to grasp in the real world. So this is similar to the grasping demo that I showed a minute ago, but this is more complex because it's a more cluttered scene and it's rigid object. So it's really like more challenging task. But surprisingly, we were able to learn how to grasp from scratch with just 600 grasp attempts, which is approximately 1.5 hours. So if you recall in the beginning of the talk, some prior work required like hundreds of hours to train a grasping strategy, right? But our work actually could learn it within just 1.5 hours. The whole system is fully automatic. You can see there are 2 bins. So the robot basically pick up object from one bin and then place them in another bin, and that automatically form a reset of the environment, and then they can shift to another shift between those 2 different bins, and then learning from its own transitions. Great. So we were very happy about this equivariant reinforcement learning, but it has some problems. First, it will require a reset and reverse function, which typically need handwritten functions in the real world, which is not very efficient. And then it's also somewhat hard to capture the multimodal distribution of robotic manipulation, right? Because if you just think about a robotic policy that try to reach some object, they actually have different trajectories that can reach the same goal, but a standard model might not be able to capture this type of multimodal distribution. In the end, we were only in XC2 active space, so we were only controlling the XY translation as well as the top-down orientation of the paper. So in the third project, we try to tackle those problems by leveraging symmetries in diffusion with diffusion models. So recently, this diffusion policy has been quite successful in robotics. Basically, it was mapping the policy learning as a noise prediction function. This is very similar to the standard diffusion models, but instead of denoising an image, we will denoise a robot trajectory. But one of the problems of this type of approach is that we are learning a function that's harder to learn compared to explicit function. For explicit policy, we just need to learn a mapping from observation to action. But now, with a diffusion model, we will need to learn a mapping from observation, noisy action, denoising step into the noise prediction, which is a larger function space. So typically, it's going to increase the amount of data that's required and increase the training time, even though the learn policy is quite good. So one question that I was asking myself while seeing this paper was that does symmetry exist in the noise prediction function epsilon? Because if it does, we will be able to use a similar strategy as before to improve on the diffusion policy learning. And the answer is yes. So here's an illustrative example, right? Imagine we have, let's say, a navigation problem where the robot in the black dots need to reach the green goalpost while avoiding the blue obstacle. So in diffusion policy, we will start from a randomly sampled trajectory and then apply a sequence of denoising steps until we have a smooth trajectory, right? So now if you think about everything rotates in the initial stage, and then what we want is all of the intermediate denoising steps to rotate accordingly, so that at the end of the denoising step, we will have the same smooth trajectory as before, but rotated. Formally, we can write the denoising function as an equivariant function. So basically, whenever the policy that we are mimicking is equivariant, we can write the denoising function as an equivariant function as well. And that way, we will be able to improve the learning efficiency for the denoising function. And here are some experimental results. So we first tested in simulation. We consider a wide range of robotic manipulation tasks, ranging from simple tasks like block stacking to very challenging tasks like coffee preparation. So first, we tested our model trained with 100 demos and compared it with different baselines. So we consider two different variations of our model. So here we consider the voxel input and image input. So the voxel input, is a reconstruction of multiple cameras in the simulation. So it's going to provide us with a more complete scene representation. Also, it's going to be somewhat perfectly symmetric because you can just rotate the voxel along the z-axis. And then for the image input, we were purely just using a third-person view, which is going to have the symmetry breaking problem that Robin just talked about in the the extrinsic case, right? Because if you rotate the image input here, you're going to see an image that's going to be out of distribution. But still, we can see both the voxel version and the image version were outperforming the baselines by quite a large margin. Especially for the voxel input, because we are mapping the symmetry perfectly, we can see a roughly 20% improvement with 100 demos. And then we also compare our models trained with more demonstrations. So here is an average over 12 different environments. We can see that our model trained with 200 demos are outperforming the baselines trained with 1,000 demos. So this is roughly a 5 times improvement in sample efficiency. And we further tested the algorithm in the real world, which is the bagel baking task that I showed in the beginning, along with some other challenging tasks like making coffee, making toaster, and so on. So in most of the cases, we were able to train a very successful policy within just tens of demonstrations. Great. So that's all from my part. And in the end, we would like to thank a lot of my our collaborators. Do you wanna? Yeah.
Here they are.
Yeah. So we have been collaborating with a lot of people, both at Northeastern and some external collaborators. None of the work will be possible without their support. And we would like to thank them. And also we are ready to take any questions you might have. Thank you.
Yeah.
Great. Yeah, so I was curious about this extrinsic equivariance. Like the bird example you gave was really interesting, and it sort of got me thinking, do you think of extrinsic equivariance as purely cases where there's literally no support in the data distribution on part of the orbit? Or do you think it's more of like continuous trade-off between being uniform over the orbit and like some other notion of like how non-uniform you are, like the entropy? Like, do you see that as a spectrum? Or...
Yeah, it's definitely a spectrum. I forget, like, we have 2 papers or 3 papers with the depth, and I forget if our actual like definition allows that, but like, I mean, in the real, like, what's the difference between if there's like a 1% density
exactly.
and 99 and 0 and 100? Like, it's not like it instantly becomes or goes away. Yeah, right.
Yeah. So in the first paper, the actual paper, we actually define it as like a yes or no question. So it's either extrinsic or incorrect or correct. But in the following up NeurReps paper, we had this spectrum. So if you remember, like Robin was showing like a crossover comparing equivariant models with standard models, right? So that's where we were able to extract different percentage of extrinsic equivariance. Yeah. So
can you remind me, was that an empirical result or was
Yeah.
it like a way of measuring?
Right. So we have both. So theoretically, we can calculate that using the data distribution. So but we were assuming that we have the data distribution, so we know for example the support over the distributions in order to calculate the theoretical bounds. And then empirically, we also designed an experiment where we were controlling the different percentage of the data that is extrinsic versus incorrect, let's say, and then just have this mixture of those different cases and then see how the models perform. So we have both. Yeah.
In general, we don't have that much like theoretical result on the hardness of learning under extrinsic or how much extrinsicness there is, so it'll be good to do more.
What sort of difficulties arise, or how do you handle cases of partial equivariance? So I'm thinking like radar and planes where up is different, up and down are different from side to side.
I see, so that would be like a case of like some symmetry breaking in the data, and so then like it's one of these in-between cases, so in that case, the relaxed equivariant models might do well. There are other ways to deal with it, like one thing you can do is if you have knowledge of like the distinctions, then you can add additional inputs to the model, which basically like if the model is aware of the symmetry breaking factors, then it means that it's definitely not an incorrect symmetry, so it'll force errors, and then the question becomes like, does including the symmetry benefit the learning efficiency at all at that point, right? It's like, how far am I from the symmetric case? Karen?
Yeah, so my question is, how do you deal with symmetry encodings in multitasking settings, and also related to this in multi-sensory settings where you have different sources of modality?
Multi-what thing?
Multi-sensory AI, where you have different modalities of inputs.
I see, yeah. Usually, I mean, like, one thing, maybe my answer would be that, like, so the nice thing about like representation theory, this kind of framework, is that it's highly abstracted. Like, so all you have to really do, like, as a practitioner, like, I want to apply this to multiple, is you have to say, I didn't really like highlight this here, but you can have the same symmetry group, but it can have lots of different group actions on lots of different spaces. So that lets you integrate different like modalities together, right? You can even like include modalities that don't have an obvious symmetry action. So but in general, the framework requires you to define it. So as long as you can say like, look, if I do this, then that will change my voxels this way, my radar signal this way. As long as you can define what the transformations are, then you can integrate them all together into the same space.
Right, but what if you're using one model where you're for several tasks, and in one task you want to be invariant towards a certain group symmetry transformation, and in another task you want to be equivariant towards.
I see. Yeah, it would be challenging to sort of like have the same model have different symmetry. You would have to, I think this maybe gets a little into the weeds, but you would have to define like a group large enough to encode all of the different types of symmetries. And then each in particular task, you essentially have to turn them kind of on or off by defining the particular representation of that group.
That makes sense.
Where are we? Lots of, okay. Maybe we'll go to that side of the room.
Thanks. I understand equivariance will make the pulse learning more data efficient, but that also means when you build in into the architecture of the neural network, that means there are fewer parameters. So do you see any issue or challenges with optimization you're learning as you're imposing more constraints?
Yeah, that's a great question. So typically we were, so whenever we compare an Equivariant network with a standard network, we will constrain the number of trainable parameters the same. But you're right, like, if we, let's say constrain the total number of parameters the same, then we're gonna have fewer free parameters. But generally speaking, I think that's not a very big issue because, we can just make the network slightly larger. So it's not gonna be like crazily larger. It's just, for example, like 2 times, 4 times larger than the standard network. Typically, I think it is okay. Yeah. We also don't see like an optimization problem. Normally, it's gonna converge faster than the standard network. Yeah.
Thanks.
I think your hand is up.
I guess I was thinking about the example where the camera was like placed 15 degrees away
Yeah.
from like the scene.
Like 15
Yeah.
degrees, yeah.
If we know that beforehand, like, is it like a thing or is it common to like, increase some transformation of the data?
Yeah. You want to start?
Oh yeah, we actually have a solution, right? So yeah, we tested that. So basically, there were multiple ways. If you have depth information, you can project the image into point cloud and then do a orthographic projection. If you do have depth, you can also use they're called homography of RGB image to try to like mimic that transformation. That works. That actually works. It's actually better than use the original image.
And then that would be like an equivariant transformation.
Yeah, exactly.
You can try to address these issues with engineering. Basically, like, the more you can make your data and your task into the sort of like perfect form that you want for an equivariant model, the more you'll benefit. But it depends on how much you know
Yeah.
ahead of time about that. Like, now you're in the wild and you've got like a spot robot, and you don't know how many
Yeah.
degrees off the camera is,
Right.
then that method may not work as well, right?
Yeah, or if we have a, online data set, they might not have recorded the camera position, then we don't have it.
More questions? Yeah, we'll go over there.
So I'm pretty curious about the approximate equivariant thing. So for us, we work with medical data, which is like super noisy. So like the equivariance assumption really breaks, and all the features that we extract with the ENNs, they're just like not equivariant in the end. So the way we model this is like, because we kind of have an idea about like what kind of noise we would expect in the data, we can train like a regular CNN to do denoising, but it's just pretty slow, and for medical application, you need things out of it.
Yeah.
So I was curious, like, to have your opinion about like if this approximate equivariance could be something like to tackle this noise problem in the data.
Yeah, it's definitely worth trying. My collaborator, Ray, with whom I developed that model, actually works for GE Healthcare now, and I don't know everything he does, but I think he posted something on the archive recently where he tried to apply relaxed equivariant models in image, like, I don't know the domain that well, but some sort of diagnostic imaging task, so.
And how does it affect the training? Like, does it become like less stable, or I don't know, a bit slower compared to like regular?
It's not too much. I actually almost think that like relaxed equivariant models are almost just better than equivariant models. It's not very many addable trainable parameters. I mean, I'm skip most of the details. We initialize the model to be equivariant, and like if the data is equivariant, it just stays equivariant at the cost of a small number of extra trainable parameters. And somehow I think maybe it actually helps optimization a little bit, since it has some relaxation in it, so it can actually maybe be a bit, it might optimize a little smoother, but I'm not 100% sure. Okay, did you have a question?
Yeah, in the example, if I understood correctly, that you mentioned two birds going up and down.
Yeah.
Domain knowledge seems important, right? Knowing that the bird will go down and this one will go up seems important.
Just like a high level amount in that case of domain knowledge, which is that like the question, in my head, the question is like, that it has to do, it kind of goes back to what Hannah was asking about earlier. There's different, like the distribution in that case, even though the task is invariant, right? The function f should give the same label, whatever rotation. The distribution of the data varies in between classes, right? And so that is, knowing that fact would be domain knowledge, right? But then the point is, if you do think your distribution varies between classes in terms of its rotational, right? Then that definitely means you're removing potentially useful information by enforcing invariance. And that now there's some crossover point, right? There's some amount where it's bad and some amount where it's not too bad.
Especially if this relaxed equivariance, do you feel if you do enough data augmentation on your normal data and then use normal network, not equivariant, it will converge further training to something similar as this relaxed equivariance or not?
That's a great question. Yeah, I don't know for sure. And I think you ask 10 different people, you'll get 10 different answers on like, it seems to be like kind of a subtle question. Seems to depend a fair bit on like what the symmetry group is, what the data types are. Sometimes you do enough data augmentation, you have a big enough model, you have enough data, then you can converge to the same thing. Sometimes not, but I haven't like specifically checked, but it's a good question.
So a quick follow-up. Would you know how to measure this?
I have some ideas, but I don't think that also is good. Yeah, I'm not exactly sure how to sort of track the alignment between the unconstrained model and the relaxed equivariant model. Did they learn the same thing? That's probably a difficult question, but you could propose some good ideas. I guess we're at time maybe. Yeah.
Are there any final questions or? Okay, if not, let's thank our speaker. Thank you all for coming.
Yeah.
Yeah, sorry, I was like, so many